Okay. Okay, so let's continue what we were discussing. I'll just do a maybe 2-minute recap and then proceed. So we are discussing the process synchronization aspect, and we have discussed why it is needed. Because when multiple processes are trying to access the same data, like same shared data, then several race conditions can arise. And we have seen an example of or demonstration of why race example can arise. That is because at any point of time, a process can be swapped out of the CPU and the CPU can be allocated to some other process. That's one reason. And the second reason is that often the operations that we write as a single statement, let's say in a high level programming language, actually get translated into multiple machine level instructions. Now, like even doing something like counter plus plus can actually mean that loading the value from a memory location to a register, then incrementing that value in that register, and then writing back that value from the register to the memory. And a process can get swapped out in between doing these three steps. Right, so we took this producer consumer problem and then we demonstrated that how a race condition can arise. And that is the need for why we need process synchronization. And more technically, this problem is called the critical section problem because it is like the way it is figured out is that there will be a critical section. A process can have a critical section where it is updating various shared variables. And we need some guarantee that only one process is executing in its critical section at a particular point of time. So this is how a process structure looks like logically, that you have this critical section and the rest of the program is the remainder section. Now, before the critical section, you need to do something in order to gain entry, or basically you need to check whether anyone else is in the critical section. If yes, you should wait. So these things should be done in an entry section. And once you gain entry into your critical section, after you complete that step, so this process should inform others that it has completed its critical section. So these things are done in the exit section. We will see several examples of these today. Okay, and we also discussed that there are several solutions to critical section problem, out of which we will study some. But a correct solution to a critical section problem should follow some properties or should satisfy some conditions, like mutual exclusion, progress, bounded waiting, and so on. Mutual exclusion is what we have already discussed, that out of n cooperating processes, only one should be allowed to execute in its critical section. Similarly, progress and bounded waiting basically say that like a process should not starve. So if a process wants to enter its critical section, then it is fine if some other process is in its critical section, then it has to wait. So suppose a process PI is already in its critical section, then others have to wait. But then it should not be the case that a particular process PI is requesting to enter its critical section, but before its request is granted, many other processes are being allowed to enter their critical section. So it's as if that PI is starving. Other processes are getting chance one after another, but PI is not getting a chance. So these kind of things should be avoided. Okay, so this is what we discussed till yesterday. Let me just proceed from then on. So in general, while discussing this chapter, we would deal with user level processes. So we will see how process synchronization happens among user level processes, but just one slide about critical section handling within the kernel or inside the OS. So there are two approaches depending on if the kernel is preemptive or non-preemptive. What does it mean? So a preemptive kernel is a situation where a process which is currently running in the kernel mode is allowed to be preempted. So preemption, I think we understand that like forcibly a process is made to get off the CPU and some other process is allocated to CPU. So as if this happens forcibly. So whether a process which is currently in its kernel mode can be preempted or not. So if it can, then it's the kernel is said to be preemptive. But if not, then the kernel is said to be non-preemptive. So in a non-preemptive kernel, a process running in the kernel mode is not allowed to be interrupted. So the process runs in its kernel mode unless or until it itself blocks or voluntarily yields the CPU. Right, and if that is the case, then race conditions cannot arise in the kernel at least. So this makes sense because when a process, it is expected that a process will spend as less time as possible in kernel mode. So all the like big computations and all should be done in the user mode itself. And a process should go into the kernel mode only when it requires some service from the kernel. And typically that time should be small. So this non-preemptive thing makes sense that assuming that processors will spend only a small amount of time in the kernel mode, do not allow preemption or within that time interval. But of course, preemptive kernels require very careful design. And so it is more suitable for real-time systems. Like normally in normal operating systems may actually prefer to deploy a non-preemptive kernel. Okay, so that was a very like high-level discussion about critical section handling within the OS. But in general, in this chapter, we will focus on user-level processes. So hopefully you have understood the critical section problem. Now let us discuss some solutions to the problem. The first solution that we discuss is a software-based solution or an algorithmic solution. And the name of this solution is called Peterson's solution or Peterson's algorithm. So this solution is restricted to two processes that alternate execution between their critical section and the remainder section. So this is typically a simple scheme which is meant only for two processes that would alternate execution between their critical section and remainder section. Also, this solution assumes that there are load and store machine language instructions which are atomic, right? That is, they cannot be interrupted. So this is an important concept which we will encounter multiple times in this chapter. We need some instructions to be atomic. That means either they will be executed or not. It cannot be that an interrupt comes or the process is preempted in between that instruction. That is not the case. Such instructions are called atomic. So we will discuss more about atomic operations. But for now, let's assume that Peterson's solution assumes that this load and store machine language instructions are atomic. Okay. Now, as I said, Peterson's solution assumes two cooperating processes. So these two cooperating processes share two variables. They can share other variables, but specifically for synchronization, they share these two variables. One is an integer called turn, which is usually initialized to 0. And another is a set of two Boolean flags, which are both initialized to false. What are the significance of these variables? The significance are as follows. The turn variable indicates whose turn it is to enter the critical section. So turn 0 would mean, say, the process P0's turn to enter the critical section, and turn equal to 1 would mean the process P1's turn to enter the critical section. I repeat that we assume only two processes, so P0 and P1. Right? This solution is meant only for two processes. And what about the flag? The flag array is used to indicate if a process is ready to enter the critical section. So flag I equal to true implies that process Pi is ready. Understand the difference? One concept is whether a process is ready to enter the critical section. A process may or may not be ready at a particular point of time. So if the process is executing in its remainder section, maybe it is not even ready to enter the critical section. That is indicated by the flag. Okay. Also, even if a particular process is ready to enter the critical section, it should not enter unless it is this process's turn to enter the critical section. So the turn variable decides which process can enter the critical section now. Maybe both are ready. Maybe both processes are ready. But then the variable turn will indicate which process can enter the critical section now. So let us study this solution now. At any point, if you have any question, please ask. So what is the algorithm for process PI? So you are first giving the generic algorithm for process PI. So this is the critical section of PI and the remainder section. So you see before the critical section, this is the entry section, this part, and this part is the exit section. This is the exit section. So both these processes are employing this kind of a structure. Okay. So what happens in the entry section? Typically flag I equal to true and turn equal to J. Okay. So let me ask a question. See these lines. What do you think is happening in the entry section? What do you think is happening in the entry section? So flag I equal to true, then turn equal to J. So what do you think is like intuitively, what do you think is going on in the entry section? So here I means this process about which we are talking, process PI, and J indicates the other process. So like if yeah, okay, maybe it might help if I show you the next slide. So this is the generic algorithm for process PI. The next slide shows the specific algorithm for process P0. So for P0, you see flag 0 equal to true and turn equal to 1. Remember the two processes are P0 and P1. So now, like what is going on in the entry section? Any answers? Okay, in the interest of time, let me describe. So okay, Ayush has an answer. Let's see. It is running in a while loop before entering critical section. Other process is trying to. Yeah, so basically what Ayush says is right. Let me explain in a bit more detail. So process P0 is first indicating that it is ready to enter the critical section. And this it is doing by setting flag 0 to true. However, it is not entering the critical section immediately. It is giving the other process a chance to enter the critical section. Right? So turn set to 1 means that P0 is giving P1 the chance to enter the critical section. So P0 is ready to enter the critical section, it indicates, but then it gives the chance to the other process to enter the critical section, turn equal to 1. And then it goes on this loop. So see there is a semicolon here. So basically this while loop is used for waiting. So as long as flag 1 is true and turn equal to 1, P0 will wait. What does this mean? So turn equal to 1 was just set by P0 itself. So it has given the chance to P1. Also flag 1 is true. That means P1 is ready to enter the critical section. So if P0 sees that P1 is ready to enter the critical section and it has given the turn to P1, then while both these conditions are true, P0 will wait. So don't miss this semicolon here. Right, so when will P0 come into the critical section? When will P0 start the critical section? When one of these two conditions is false. So either flag 1 is false, that means P1 does not even want to enter the critical section, or turn is 0. In one of those cases, P0 will enter the critical section. Okay. And after executing the critical section, it will set flag 0 to false. That means it no longer wants to enter the critical section. Okay. So this is what P0 does, and just as a mirror image, this is what P1 does. The next slide. This is what P1 does. It indicates that it is ready to enter the critical section, but then it gives P0 the turn to enter the critical section. Okay. And as long as P0, so how can P1 know that P0 is in the critical section? It assumes that first it says flag 0 is true. So P0 was also ready to enter the critical section. And P1 has given the chance to P0 by setting turn equal to 0. So as long as both these are true, P1 will wait. Okay. So when one of these conditions become false, then P1 will enter the critical section. And after executing it, it will set flag 1 equal to false. Now see the synchrony between these two processes. Remember, these are cooperating processes, right? So see the synchrony between these two processes. Say P1 gives P0 the chance to enter the critical section by setting turn equal to 0. Okay. As long as these condition is true, these two conditions are true, it will wait, with the assumption that P0 has entered its critical section. Now, going back, this is the slide for P0. P0, after it has completed its critical section, will make flag 0 equal to false. And this will make P1, so flag 0 will become false, and this will make P1 come out of this while loop and enter its critical section. Okay, so basically P0 is giving so P1, you might look at it in any way. P1 initially is giving a chance for P0 to enter the critical section. P0, when it is completing the critical section in the other slide, P0 when it is completing its critical section is making flag 0 equal to false, and this is an indication for P1 that now it can enter the critical section because flag 0 has become false. Okay, so this is how P0 and P1 are cooperating. Any questions here? Yes, Ayush has a good point. So the while condition evaluates to false only because of this flag, because see, turn has been set to 0 here only. Right, turn has been set to 0 here only. So this condition must be true. Of course, it can happen, like when can turn be set to 1? See, P1 is never setting turn to 1. Right, P1 is never setting turn to 1. Who will set turn to 1? If anyone, then P0 here. Right. So P1, you are right. So P1 will never set turn to 1. That will only be done by P0. So it can happen that suppose P0 completed its critical section, then it set flag 0 equal to false. Then it circled around because the whole thing is happening in a while loop, right? The whole thing is happening in a while loop. So flag 0 was set to false. Then it circled around and came here. If so, then flag 0 would be true again, and then turn equal to 1. Right, so assume that all these things can happen while P1 was waiting. So then when P1 comes here, it will see at some point. Okay, tell me if you are confused. I'm saying that suppose P0 has executed its critical section once. Okay. After that, it will make flag 0 equal to false. Maybe it circles around and comes here. But then it will not try to immediately enter the critical section again. It will make turn equal to 1. Okay. And because it makes turn equal to 1, at some point, P1 will find this while loop false, and therefore it will enter the critical section. So typically there will be a alternative execution of critical section. Like P1 will every time, like before P1 enters the critical section, it will give the chance to P0 and vice versa. Is this clear or any other question? Yes, both turn and flag are shared data. Let me go back. Yeah, the two processes share these variables, turn and flag. So turn and flag both are shared between these processes. Any other question? Okay, let me proceed. So yeah, so this slide gives the generic algorithm in terms of PI, but then the next two slides give the more specific algorithm of P0 and P1. Try to understand how P0 and P1 are cooperating. So you will see that by means of this flag and turn, they are ensuring that they alternately get a chance to enter the critical section. Because before entering, so both these processes or each process before entering its critical section gives the other process chance to enter the critical section. Okay. By the way, so one thing, let me ask a question. So in this scheme, can it be that P1 enters the critical section twice consecutively without P0 entering even once? Can it be? Okay, think about it. I got two answers as no. Does anyone think yes? Depends on when each process gets the CPU. I'm not sure. So Srihash, maybe can you unmute yourself? What do you mean?
Yes, sir. Basically, if the process P0 does not intend to enter the critical section, basically if it's spending a lot of time in the remainder section,
Exactly.
P1 gets enough time to run a second iteration of the loop, it will enter the critical section.
Yeah, right. So let's see what Srihash said. See, this flag variable is only, so flag 1 is only set by P1 and flag 0 is only set by P0. Okay. Now suppose that it is like this, that P0's remainder section is very long and P1's remainder section is very small. So once P0 has completed its critical section, it sets flag 0 to false and then it goes into the remainder section. Flag 0 will not be set to true until and unless P0 again starts executing from here. Let me repeat. P0 has set flag 0 to false and then it has gone into the remainder section. Assume that it takes a lot of time in the remainder section. So flag 0 is false and flag 0 will not be set to true until and unless this whole while loop completes and P0 again starts executing here. Right? So flag 0 is false. Now let's say P1 has a very small remainder section. So P1 enters its critical section, sets flag 1 equal to false, quickly completes its remainder section, circles around, sets flag 1 equal to true, turn equal to 0. Now when it comes to this while condition, it will check for flag 0, which is still 0 because P0 is still executing its remainder section. So even though P1 gave that chance to P0 by setting turn equal to 0, P0 did not want to take that chance because flag 0 is still 0 or flag 0 is still false. So then P1 does not need to wait. It will immediately enter the critical section. Okay. So if it is the case that let's say P0 has a long remainder section and P1 has a very small remainder section, it can happen that P1 enters the critical section twice without P0 even trying to enter the critical section even once in between. Okay. So any doubts, any questions? Okay, let me proceed then. Yeah. So this Peterson's solution, this is one valid solution of the critical section problem, though with some caveat, which we are going to discuss. But basically it is provable that all the three requirements of control section critical section problem are satisfied. So mutual exclusion is preserved, progress requirement is satisfied, and bounded waiting requirement is also met. I'm not going to discuss the proof here. The textbook gives gives us rough sketch of the proof, so please go through it. But yeah, it can be proved that Peterson solution meets all these three requirements. Though yes, Peterson solution is applicable only to two processes, and there is another caveat which we will just discuss next. Okay, so the caveat is that this. So you have done a COA course, and then you know that due to pipelining, etc., nowadays computer architectures allow out of order execution. Right? So I think this has been covered in COA. Like you know that due to pipelining issues and all, statements in the same program itself can be executed out of order. This you know, right? Yeah. So Yeah, due to pipelining and all these things happen, and therein comes a problem. So there is no guarantee that Peterson's solution will work correctly on such architectures which allow out of order execution. So let's demonstrate that. So this is the code for P0, not the full thing, but a part. And this is the code for P1. See these two statements which are marked in red. Assume that they are executed out of order. That means turn equal to 1 gets executed before flag 0 equal to true, and turn equal to 0 gets executed before flag 1 equal to true. Assume that this happens due to out of order execution. In that case, what can happen? Let's see. Right? So assuming that these two happens out of order, this turn equal to 1 happens first and turn equal to 0 happens first. I mean, first means before this is. This can happen. Look at this order of execution. So say P1 sets turn equal to 0. P1 sets turn equal to 0. So this happens first, right? Out of order execution. And then there is a context switch. P0 comes in. So P0 is allocated to the processor. P0 now initiates makes turn equal to 1 out of order execution. Then it goes to flag equal to 0. Sorry, flag 0 equal to true. And then when it comes to the while loop, it sees the turn equal to 1 and flag 1 is 0 or flag 1 is false. Remember, both flag variables are initialized to false, right? So let's say flag 0 has been made true, but then flag 1 has not been made true yet, right? Because remember, P1 only executed this turn equal to 0 instruction. After that, there was a context switch. So P1 has not executed this statement yet. Okay, there was out of order execution. So P0 just could execute this instruction turn equal to 0, and then it got swapped out. So now P0 comes and does turn equal to 1 and then flag 0 equal to true. But then it checks the while loop, this one. And flag 1 is still set to 0 or false because P1 has not changed it. So since flag 1 is false, P0 directly comes out of the while loop and enters the critical section. Okay. Now let's say P0 is swapped out of the CPU and P1 is allocated the CPU. So now P1 comes and executes this instruction flag 1 equal to true. Then when it comes to its own while loop, it sees flag 0 is true, but turn is 1. Turn is 1. Okay. It also comes out of the while loop and enters the critical section. So now both P0 and P1 has entered the critical section. And this happened because of out of turn execution, right? So specifically, this instruction of P1 got executed before this one was executed. So therein lies the problem why Peterson's solution is not guaranteed to be correct in such architectures which allow out of order execution. Convince yourself and tell me if you have any questions. Okay, if not good, let me proceed. Yeah, so Peterson's solution, remember it's a completely software solution. I mean, that means an algorithmic solution. However, it is not guaranteed to be correct in such architectures which allow out of order execution. Okay, so then what is nowadays done? So nowadays with such processors which deploy pipelining and out of order execution, Peterson's algorithm will not be enough. So what is done? Let's discuss that. So nowadays, most systems provide hardware support for implementing critical section code. So what we are going to discuss from now on are all discussed on the are all based on the idea of locking. right? So I think someone actually mentioned it yesterday that can't we lock? Sure, that is exactly what is done. So the idea is to protect critical regions via locks. So of course, how to lock something? One idea, which again, yesterday some of you suggested, is to disable interrupts. Like as long as a particular process is in a critical section, do not allow it to be swept out. Disable interrupts. I mean, as long as a process is in its critical section, do not allow preemption. But then this would be too inefficient. As in, I mean, nowadays we don't want that. More and more multi-programming, or we want the processor to be shared among many processes. So then we will use this idea of locks and some atomic hardware instructions. So the atomic term means non-interruptible. That means a particular operation which once started will complete. I think this concept of atomic operation you have studied in another course. Anyone remembers? In any other course, have you come across something called atomic operation? Okay, have you all done a database course? Okay, you are doing this semester. Fine. Okay, so maybe in database also you will find something called atomic operations. I mean, just to give you an idea, let's say, I mean, this is not operating system. Just to give you an idea, like say a bank transaction is going on. So let's say X has, yeah, exactly, atomic transaction. So let's say a bank transaction is going on. So 50,000 rupees would be transferred from the account of X to Y. Now let's say 50,000 rupees were debited from the account of X, but before it could be credited to Y, something went wrong, right? So in this state, like X, 50,000 rupees has been debited from X, but nothing has been credited to Y. This is a bad situation for the system to fail. So typically this should not happen. So a transaction should be atomic. Either it won't be at all started, or if it is started, it should complete. So it should not be that 50,000 rupees were taken out from X's account, but then nothing was added to Y. Right? Either it should not happen at all, transaction can fail, okay. Or if it starts, it should complete. So I think you will come across atomic transactions in database also. But okay, here also the idea is kind of simple. I mean similar, that these are atomic hardware instructions. Either they will not happen at all, or if the instruction execution starts, it will complete. In between, there will be no interrupts, preemption, etc. Typically, these are very simple instructions. Like we'll see some examples, but yeah, these are special instructions provided by the hardware, which are guaranteed to be atomic. Now let's see what kind of instructions. Okay, so if you have this kind of an instruction, then the general structure of the solution would be like this. Before the critical section, you will use this kind of an atomic operation to acquire a lock. And after you are done with the critical section, you will use another atomic operation to release the lock. Right? So simple. I mean, if you have this kind of an instruction which is atomic, just use it to acquire a lock and release a lock. Right? Now let us see some actual such atomic instructions. One is test and set. Right? Test and set. So as the name implies, it's simple. Test a particular Boolean flag, let's say target. Test whether it's 1 or 0, and set it. Set means set to true. Okay, and return the previous value. So basically returns the original value of the parameter target and set the new value of the parameter to true. Okay, returns the older value and sets it to true. Importantly, this whole thing would be done atomically. I mean, either it will happen or it won't. There will be no preemption at this point. Let's say just after this happens, there is a preemption that won't happen. Okay, so the whole thing would be done atomically. Okay. Now, some of you might wonder that, hey, seems there are two instructions, then how can the two be atomic? The idea is not that. So here, just for ease of explanation, we abstracted out the functionality so that it looks like a C function. But in practice, there can be a single low-level instruction for this. So for example, in the MIPS architecture, we can have a machine instruction like this, TAS R1 this. So essentially this means these two steps will happen atomically. So the location of memory, the value of memory location 1000 will be stored in R1, and then memory location 1000 would be made 1. Test and set. These two will happen atomically. There will be no preemption, etc. in between these two instructions. So because actually this is one instruction. I mean, again, this is just for explanation, this part. This is the one instruction. Okay, so the architecture guarantees that this will happen atomically. This is test and set instruction. So now suppose you have such a test and set instruction, an atomic one, then how can you use it as a lock? Simple. Have a shared variable lock initialized to false. So false indicates unlocked. So each cooperating process does this while test and set lock. So this is in a while loop itself, right? So while this, do nothing. So what is going on here? What is this doing actually? This statement, what is it doing? So like, is it trying to set the lock? Actually, yes. So this instruction here, this is trying to set the lock. And as long as it is not able to set the lock, it will wait. Once the lock is set, that means no other process will be able to set the same lock, and then it can enter the critical section. And after having done with the critical section, it makes lock equal to false. Okay. Any questions here? So test and set is a special hardware instruction which is guaranteed to be atomic. And if you have such an instruction, this is how you can use it to set a lock or to acquire a lock before entering a critical section. See, once one particular process has set the lock, no other process can set it unless it becomes false again. Just a minute. Yeah, so okay, so Sriyash has a question. Why don't these processes give up the CPU inside the while loop? The busy waiting seems wasteful. Okay, excellent question. So Sriyash, can you unmute yourself?
Yes, sir.
Yeah, so it's a very good question, but can you clarify what is your issue here?
Right. So basically, if another process is already in its critical section, and let's say it gets preempted and this process tries to access the critical section. It realizes that, okay, the critical section is not allowed for me to go in. So it keeps checking this condition again and again in its time that's allotted to it instead of yielding to the CPU, yielding to another process basically. So why are we testing this condition multiple times when we know that it's not going to change until another process gets the CPU, basically?
Okay, and you used the term busy waiting. Like, where have you heard this term, or like?
From the assignment, we had a previous
Okay.
assignment.
Yes. Yeah, very good question. That is a known issue about these locks, that CPU cycles are getting wasted. Right. So maybe one process is in its critical section and the lock is set. So then another process, if it is allocated the CPU, so in this while loop, basically it's wasting several CPU cycles. It is going on trying to set the lock. But I mean, what would have been better is if check the lock once. If you find it's already set by someone else, sleep for some time, as it don't do anything. But get out from the CPU. Okay, so yeah, actually this is called busy waiting. We will come to this in a subsequent slide, but yeah, so typically this is not the most efficient way of doing it, but at least it's correct, right? So yeah, very good question, Shreya. So it's not an efficient way of doing things, because ideally we would not like processes to just go on a like kind of a loop doing nothing, because that wastes CPU cycles. And CPU is our most important resource, so we don't want to waste cycles. But at least it's correct. So if you have such an instruction, you can do it. Okay. So if one process has already set the lock, the others cannot set it. Okay. So just one thing here. Okay, let me go back here to this definition of test and set. As I said, so I made this statement that if one process has set the lock, the other process should not be able to set it. But then here there is no if statement, etc. So how is this happening? Like, how are we ensuring that if one process has set the lock, no other process should set it, etc. How are we managing this? Because this does not have any if statement. So why are we claiming that this is working? I hope my question is clear. If not, then I mean, sure, you can even ask me to clarify the question. Typically, this kind of a code will be used by all cooperating processes. But nowhere is this kind of a code written that if the lock is already set, then don't, etc. So there is no if here, right? There is no if here at all. So how are things getting managed? Exactly. Again, what Srihash is telling is correct. The return value is the current value of the lock. So see, that is why the return is there. Otherwise, it could have been just set the value to, set the value of lock to true. But then apart from trying to set this to true, the older value is returned, or the original value is returned. So it's the responsibility of this process itself to check. If this returns true, that means the lock was already set. So this process should wait. And if the lock was not set, then this will return false. Then it's okay, as in the process can actually set it. So automatically the lock has been set to true. And now this process can go in the critical section. But so it is important to note why this previous value was being returned. Right. This is what will tell this process whether the lock was already set or not. Is this clear? Okay, moving on. Okay, I have a, yeah, moving on. Just like this test and set instruction, there is another such atomic instruction, which is called compare and swap. Okay. So compare and swap looks like this. Here you see that is actually a if statement here. There is actually an if. So like what we were discussing, that is explicitly done here. So what does this compare and swap do? It returns the original value of the past parameter value. Also, the variable value is set, the new value, only if value was expected value. That is, the swap takes place only under this condition, right? So here two values are passed, expected and new value. So first there will be a check. If value is expected, then the new value will be assigned to value. Okay, and the older value will be returned. So now there is this explicit if check, which was not there in test and set. So now if you have this compare and swap instruction, how can you use it to acquire a lock? Oh, by the way, before going there again, remember that this we are showing just to explain. We are writing it out as a C function kind of thing. But in practice, there will be a single low-level instruction, something like this. And how this will be interpreted is this, that if this register 1 equals the memory location 1000, then the memory location 1000 will be set to the value of R2. Okay, so this is the expected value, and this is the new value in terms of this function. The way it is written here, R1 is the expected value, so it will be checked if the value of the lock or the value was the expected value. If so, the new value, which is R2, will be set. I mean, the value will be set to R2. And if you have this kind of an instruction, then how can you use it to solve the critical section problem? Again, simple. This is what you will do. So you see here expected value is 0 and the new value is 1. So basically this is trying to set the lock to 1 provided that the current value is 0. If the current value is not 0, then the lock won't be set because it's already set by some other process, right? So if the existing or if the current value is 0, then if the value is already 1, then compare and swap will not work because we are sending it with an expected value of 0. Only if the value of lock is 0 now, it will be set to 1 and 0 will be returned. So that is what is being checked here. Let me go back to that function. See, the expected value is the second argument and the new value is the third argument, right? And what is returned is the original value of this, right? And this change happens only if the original value was expected. So here we are calling with an expected value of 0. So the change in the variable lock will only happen if its original value was 0. In that case, it will be set to 1 and 0 will be returned. So that is what is being checked here. And as long as this does not happen, again, it will do nothing. So again, busy waiting. If this succeeds, so this process has succeeded in setting the lock to 1, then it will enter the critical section, etc. Okay. Any questions? Okay, just a couple of slides more because this is something that So remember that we have discussed several properties or requirements for the critical section problem: mutual exclusion, progress, bounded waiting. that what we studied earlier, like test and set and compare and swap, may satisfy mutual exclusion, but may not satisfy bounded weighting. Okay. So next slide shows another algorithm using test and set that satisfies all critical section arguments. So this is the algorithm. I'm not describing it here, but you will find this a description of this in the book. Right, so go through it. Right. Okay, so till now we have discussed a software solution, which is Peterson's algorithm, and two hardware solutions. I mean, you can say two, or maybe basically atomic hardware instructions, of which we studied two, like test and set and compare and swap. Okay. Next, we will start mutex locks. So yeah, let's do that next in the next class. Okay. So any questions? Okay, if not, let's end the class. I appreciate that some of you attended this makeup class also. I mean, this will be recorded, so hopefully the others can also see it. Okay, then, thanks. A small feedback. How was the test today? Like, how was the question? As in, you can unmute yourself and say, like, how was it? Like, too difficult or okay, too easy? Too easy, right? Okay, Srihash, how did you feel?
It was fine, sir. I think it was appropriate.
Yeah, it was quite easy actually, right? And okay, the more important question is the setting is okay, as in keeping your video on, then scanning things and uploading, manageable?
I think that added to the tension more than the test.
Yeah, online exams, that's the problem. But at least I think, like, apart from one or two students, I think all of you managed, which was good. Okay, let's see. But at least maybe this was the first time you were doing it. But hopefully the next few times you won't be so much tensed as the first time. But overall, yeah, it went smoothly, I think. Yeah. Okay, thanks everyone. We'll continue in our like normal class on Wednesday.